Thank you very much. So thanks again for the introduction. Today I want to talk about on a broad range of topic, mainly in the field of AI, because this is the leading motor in, I would say, digital health at the moment. And my research group works on these kind of topics, and not only my research groups, of course, many different groups in Heidelberg, and also in the consortia we are part of, which is called Informatics for Life. You can see the logo here on top. Informatics for Life is basically a consortium that was between mathematicians, computer scientists, different clinicians from the field of cardiology and cardiac surgery. And we deal with all sorts of topics from simulation to genomics to image processing, computer-assisted surgery. And I will touch upon a couple of these topics today. And hopefully I can give you an overview, but of course this will be never a comprehensive overview. There are so many different things going on here on the campus. Let me see how I change to the next. Oh, okay. So you've probably heard that just recently, basically just this month, the new surgical department at Heidelberg University opened, that you can see here. And it's considered as the most modern surgical clinic in Europe, because many different novel concepts were realized there. For example, integrated operating rooms. I will speak about them today a little bit. And also, not only there was this new opening of the surgical clinic, there are plans for building a novel heart center in Heidelberg, and the plan is to open this around 2024, 2025. And also there, many new digital concepts should be integrated, and also research groups such as my research group will be probably based in this building, hopefully. So we, as computer scientists, we will work very closely with the clinicians. And the question is, what is actually what do you consider as a modern hospital? And I would say it's, of course, not only image processing, where AI is very good in, but there's also a big potential improvement that can be made in the field of process workflow management. So when a patient is admitted to a hospital, some kind of therapy conducted on the patient, for example, surgery, then the patient is monitored and finally discharged from the hospital. But in this now here, what appears a quite linear process for the patient, there is a complex interaction of different stakeholders behind the scenes, between operating room personnel that works on the ICUs, in the sterilization departments, in the imaging facilities, or cleaning personnel, and everything has to be somehow managed. And surprisingly, most of the communication is still via a good old-fashioned phone today. So there's a lot of room for improvement when you talk about process optimization in terms of better time scheduling, making resources available at the right time, which can improve efficacy for the whole clinic, basically. But on this way, many different problems have to be solved, huge problems, basically. Or basically, the first problem is, how can we acquire the information in a digital way? The second big problem to solve is, how can we integrate different databases such that we have the right information at the right time? And how can we retrieve that information as well? And we had a specific Let me just wait 1 second, because I always see this part coming in. It's a little bit annoying. Sometimes I do not see the slides. How can I disable it? Okay, I don't know.
Which part is it? Is it
it's
the
just
people coming into the room?
Yeah, the people coming into the room, and the bar is coming into my window all the time.
Maybe if we, I mean,
it's fine.
If you switch her from co-host to
fixierte mit, I think I found it.
Okay,
it's fine. Sorry for the
Okay.
I'm very sorry for the interruption now, but it was really annoying because I did not see the slides.
Okay.
And so we have been not looking into process workflow management support in a global way, because you somehow have to start at some point. But we are looking specifically into the operating rooms. And integrated operating room an integrated operating room, that means that basically the devices in the org are connected somehow to each other, and you can assess different data streams from them. For example, from surgical devices such as camera, insufflator devices, or lights from the ceiling. And the purpose is to record such kind of data and to analyze such kind of data is to get an awareness in which kind of phase, for example, the surgeon is currently is. You could visualize context-sensitive information during a specific phase, or we could specify what is the most probable tool that is required next for the surgeon. And you could also determine the remaining duration time of surgery. So there have been works that considering that. It's quite fascinating. From our side, we are looking into. Oh, can you still hear me?
Yes,
Okay,
we
because
can.
somehow
the slides disappeared.
Yeah. Somehow my PowerPoint just crashed. That never happened. I'm very sorry for this.
That's no problem.
That's okay. It's back.
Okay, we are back on track now. Okay. We are looking mainly into surgical phase visualization, and here is some kind of visualization on the right-hand side. So you see the duration of the surgery plotted as a bar, and the specific phases are basically color-coded. There are like 6 to 7 phases per surgery, and you can already see on this very initial representation that basically the phases of the surgery can be quite different between when you compare two different surgeries. For example, in this case, you see a quite linear, I would say, course through the surgery. But in other cases, you see that some phases are interchanging a lot. And we try to look more into this data, basically, for example, to detect rare events that occur during surgeries or specific patterns that only specific surgeons are using. And here's a more detailed view on some kind of data streams we can obtain or we can annotate, basically. So when we look then much closer into one bar here, we can, for example, get more information about the operating room lights, the endoscopic light sources, the endoscope itself, or the insufflator that was used, and what was the current gas rate that's plotted here on top. And we can also, from the endoscopic image stream, we can determine what kind of instruments are used during which phases, and which instruments are used together, for example, in which phase. So here are 2 examples of 2 specific phases, and you can see that the instrument usage during the OR in the specific phases are quite different. For example, here in this surgery, the ligature is used over the course of time, basically. And here there's a lot of interchange between the single instruments. And basically what we can see from this kind of visualization is that we can use, for example, the information about instrument occurrence can help us to define the phase as well. One approach is basically to analyze the endoscopic stream, as you can see here on the right-hand side. You can do this with deep learning technologies, with artificial neural networks to, for example, detect where an instrument is on the image and then classify it. And there are many works that deal with that. This is just one example. And that has been used also for remaining OR time prediction, or analysis can be used for also analysis instrument wear out, when you see that one instrument is used a lot and you just look at the lifetime of one instrument. So, and what I want to say is that, of course, you cannot analyze these data sets manually. So machine learning, deep learning methods come into play here, and they might support image analysis. But when we consider the clinical reality, of course, we have a lot of surgeries are conducted every day. We can basically record many different data sets. So the clinical data sets are plenty, but often you have the problems that the images are not, or data sets are not standardized, they're not structured, the data sets are missing. It can be quite heterogeneous because of multiple reasons, because of the image format, or the patient itself, the patient anatomy, patient-specific anatomy. They can be distributed in different warehouses, so it's quite difficult to assess those data sets. And also on top of that, if we speak about supervised neural network approaches, then we need a lot of annotations. And as you know, obtaining those annotations is usually very expensive, because you need a clinician to do these annotations. For example, on a medical data set to segment the liver or the heart. This can be only done by a clinician, and should not be done, of course, by a novice like me, for example. And so therefore, such annotations are also scarce and not so much available because they are expensive to obtain. And we have specific, really specific hurdles to overcome here. And because of this situation, we often observe, we have a limited amount of training data, and we often observe some kind of gap between the distribution that was learned from the training data set and where our model is actually applied on. And that's a huge problem. And I want to talk about some examples how we can overcome this gap a little bit. I don't think that we can close this gap entirely, but at the end of this talk, I will give you some insights what I think we should do next in this field. So I will talk about in the next couple of minutes, how can we efficiently generate new realistic data, and how can we efficiently reuse existing annotations. And the first example is about an example that tried to close this domain gap from a real simulation to another real data set. You will see what I mean with this in a couple of seconds. So what are AI techniques currently capable of? So I like this example a lot. I have it from Memo Acton. Thank you very much. So what the network learns, basically, it learns to translate, and I hope you can see my mouse cursor somehow. It learns to translate the scene, what you see on the left-hand side, to an image representation, so to such beautiful images on the right-hand side. So it basically learns how to translate the one domain into the other, and vice versa. And exactly this kind of technique we use also in our applications. And the technique you are using are usually conditional generative adversarial networks. And they convert some kind of high-level descriptions of a scene. This can be a segmentation map, an edge map, another abstraction. We just saw a real abstraction, I would say. And you train a network that fills in the details and basically returns a more detailed scene. But it has, of course, needs many training samples from this detailed scene. For example, in this scenario, it would need to know how a sea looks like and maybe a beach or something in order to be able to generate such images. And this is basically an approach that goes back to a seminal paper from Philip Isolar called Image-to-Image Translation with Conditional Adversarial Networks. I don't want to go into detail here much, but if you want to try it out, there's also a really nice tutorial in that you can just follow this link and play around a little bit with that. So you can see that these approaches were able to convert such segmentation maps into real street scenes or such edge representations into a real handbag. I'm sure you heard about this somehow in the media before. And that was in the year 2018 in December, where NVIDIA invented the AI interactive graphics at the conference and presented it as the conference NeurIPS 2018. They rely on the same technology basically in order to make a virtual scene more realistic. And they say, also this research is early stage, application of this technology promised to make it much cheaper and easier to create virtual environments for many different domains. Interestingly, we have used this same technology or a similar technique, but we applied it in an augmented reality case. And I wanted to show you in some kinds of seconds how we did this. First, the clinical use case. I don't know, you're probably not so familiar with mitral valve repair. So mitral valve is a heart valve, and that this is a surgery. So the valve is repaired during the surgery to make it competent again, basically. And you see some examples here how the valve can look like. And these scenes are super diverse. You see different sutures, you see different tissues. In some cases, there's more blood. Here is a prosthesis. So this is how these scenes look like intraoperatively. So this is what a surgeon would see. And doing mitral valve repair, this is a very demanding surgery, I must say, because the surgeon has to follow many different steps, and it's very experience-based. And also they have to use long-shafted instruments. They're not really used to this in other clinical application or in other surgeries. So it's quite demanding, I would say, for the surgeon to do this surgery. And therefore, we developed the training simulator that you can see here. And the simulator basically extracts, or in order to produce these kind of representations you see here, we use ultrasound data, echocardiographic data, we segment this, and then we came up with a production process to bring these patient-specific models into life, basically. And they are made of silicon. And the surgeons are quite satisfied with the simulator. We had many cardiac surgeons already for training on the simulator, basically. And they are quite satisfied with the shape and the material, the stitching and cutting properties of the material. But they're not so satisfied, of course, with the appearance. So we see a silicon surface that does not resemble the intraoperative complexity, I would say. So we do not see the heterogeneous texture or specularities or blood at all. And therefore, we came up with the idea to use this AI concept on a simulator. Let me just explain it to you. So we have here, this is our simulator, and you see there's a valve inside, fixated inside. And there's an endoscope that captures the information, the view basically also the surgeon has. And then we use this current image, we feed this into a deep learning network, and we basically present to the surgeon a more realistic image on the screen. And we coined this as hyperrealism, as a novel form of augmented reality. Why do we think this is augmented reality in this setting? Well, as you know, in traditional augmented reality, you basically overlay virtual objects on a real scene. In our case, it's a little bit different. So we replace the whole image. But we can say some parts of the image actually should stay the same, while other parts should be replaced by the neural network. And so, for example, the needle and the sutures and the instruments, they are the same in both domains, basically, or very similar in both domains. But mainly the background and the valve itself should be rendered more realistic. And when we apply this very basic technique, it's not so easily distinguishable what is actually a real image and a fake image. And I could ask you now what images you think are real and which one are fake. I think we go on a little bit now. So these are the fake images, and I would say they are not so easily distinguishable from the real ones. And some more examples here. I have some more examples here. Okay, it's not working. Cannot. Okay, now figured it out. So you basically see it here on a video, and the approach works quite well, but for some scenes it's more difficult. For example, when the instrument comes in, but apart from that, it's quite stable. So we worked on this to remove the flickering, because if you transform individual frames one by one, that results in a lot of flickering. So we developed a method to overcome this flickering a little bit. And this is just another scene. And what you also see, what I found quite funny, is that here the sutures are turned red, because this is also happening during surgery. So the network learned it intrinsically that intraoperative sutures are usually a little bit more red. This is no clinical. This is not absolutely not meaningful for a clinician, but it's interesting that the network was able to learn that. And for future tasks, we are currently looking into other things. For example, analyzing the stitching patterns for annuloplasty ring implantation, so for the prosthesis that is sewed onto the annulus, on the simulator and also on the intraoperative case. And of course, you see that there's quite a domain gap between these two. But with our approach, we are able to close this domain gap a little bit, and we want to look into that a little bit more in the future. And also we can use these suture points to superimpose other relevant information, for example, on the ring prosthesis is now here shown in an AR setting, in an augmented reality setting, in order to determine which kind of ring might be the best one for the patient. We are also using the simulator now for actually clinical, for surgical planning. So we have surgeons one day before the actual surgery takes place on our simulator, and they somehow rehearse and try to lay out the strategy for the upcoming day already on our simulator. And then after the surgery, we ask, do you think the simulator was realistic enough to capture the complexity, etc. But this is an ongoing study. Here you see some further examples from our from the simulator. And I guess I skipped the next two slides, so the surgeon was not quite sure whether to select 36 or 38 sized ring. These are the ring sizes, and tried this out on the simulator, so that was quite nice. Okay, now I want to capture or come to another example. of domain transfer from virtual to real. It basically uses the same technology or the same underlying method I've been talking about, but it applies it to a laparoscopic use case, so for the liver, and it applies it to a virtual scene. And so we are not converting from real to real, we're converting from virtual to real. And the goal here was to generate realistic synthetic laparoscopic data. And the advantage of this is that, of course, virtual data has perfect annotations, so we can basically generate all sorts of annotations from our virtual scene, whether these are segmentation maps, edge maps, etc. And there are also no privacy issues related to these kind of data sets. And here you can see some examples. So from one instance, we are able to simulate many different textures. And what's also the purpose of this? So the data set, this work has not been done by us. It was mainly done by Stefanie Speidel. We just collaborated a little bit on this project. And the group has released all the data sets you can see here, and they can be used for further training now. Deep learning models that solve different tasks, for example, segmentations or depth estimations, etc. So if you are interested in, you can download this data set. And now coming to other methods, how to close the domain gap, for example, data and domain adaptation and transfer learning. And we look now a little bit more into more traditional image processing techniques, I would say. So I work in this Informatics for Life consortium, for example. We work with cardiac MRI data that you can see here. So this is the heart, which is here highlighted, the left ventricle, the right ventricle, and the myocardium. And this is a typical 2D multi-stack cardiac magnetic resonance image, because you see that it has a high in-plane resolution, but it has a low out-of-plane resolution or a high slice thickness, meaning that the voxels are highly isotropic. And this is a little bit challenging for training 3D networks. Therefore, most of the processing is done by 2D neural networks, mostly by the UNet. I'm sure you heard of it, which is now the de facto standard, I would almost say, for image segmentation. So we did not invent this, of course, but it was introduced by Olaf Ronneberger years ago, and it has shown its superiority in many different applications, and we're also using it. But of course, there's still, depending on the training set where you train your model on, and then where you apply your model on, there can still be a huge domain gap, and we try to assess this gap. And so we try to evaluate the robustness of the segmentation model. How robust is it within the heart? How robust is it to other pathologies? And how robust is it to other slice orientations? Within the heart, what is very typical is that these networks are very good at segmenting the middle part of these images, but they often fail to capture the apex, which is some kind of tip of the heart, and the basal slides in a very good way. So we have a lot of different results basically in these areas, unfortunately. And there's also the question, can we actually apply networks that are trained on a huge database to rare diseases such as congenital heart diseases, which are quite different to a normal anatomy? And we asked us this question and tried to basically evaluate that. So the input was we trained it on a public data set with different pathologies from adult cardiology. And we will question ourselves, can we apply this model to unseen rare pathologies, such as here TOF means tetralogy of Fallot, which is a congenital heart disease. And what we can see is that there's quite a big domain gap between when we just apply this model to unseen data sets in this case. And that poses, of course, for the introduction of this kind of models into clinical routine, these poses many challenges, because, of course, you want to have robust models, you want to have output that you can trust. And then we went one step further and asked ourselves, what if we have rare disease in the data sets, and what if we have an unusual image protocol, for example, not capturing the heart from usual, that means short axis orientation, but from an axial orientation. And you see that the heart looks quite different in this orientation. And we tried to use basically a network that was trained on these ZAX images and apply the domain adaptation technique to such that such orientations are also segmented quite good. And I'm just looking at the time a little bit. I think I won't go so much into detail here how we did this, but the basic idea here is that we taught the network to learn how to transform the data set, how to rotate the slices such that they look like in a short axis orientation, and then we basically transform it back. Another, and this is my last example here, another approach we have been investigating was transfer learning. And that was also very interesting. So I've been looking into, can we use a huge database from traditional computer vision, for example, ImageNet, and can we actually use this for classification? Or can we actually use this for segmentation? So that model was used on a classification task. And the advantage of this is that this model has seen millions of data sets, while we have in the medical domain often only a couple of hundred. And we tried to pose a transfer learning question here. Can we reuse the learned weights from these networks in order to solve a completely different task, which is an image segmentation task on a completely different domain? And we found out that if we do this, this enables definitely the training of deeper networks that did not converge beforehand. So that is one advantage. So I've shown you some AI methods, and I hope I could give you some insights in the field of endoscopy and MRI, basically cardiac MRI, basically showing how to efficiently reuse existing annotations by domain adaptation and transfer learning, and how to generate new realistic data with generative adversarial networks. But I think these results are nice, but we have to consider, we have to be very careful. All machine learning and data learning approaches are data-driven. And as we know, data is flawed in real-world applications. And all the approaches I've shown can only partly close this domain gap we see. And another problem is that these networks often make, like in a supervised fashion, overconfident decisions, meaning, for example, that they would classify, if you have an image and you apply some kind of different noise pattern, the same image might be classified into another category than beforehand. And that's a huge problem for the applicability of these models. So future tasks, I would say, are we need to increase the transparency of these of the network's decisions and of the network outputs. We have to look into much more into uncertainty, data uncertainty and model uncertainty, or we need to conduct an out-of-distribution analysis. For example, when a test set is shown to a network such that the user is alerted, okay, this sample is very far from the training distribution. Please be careful with the result. I think this is very, very important that we from a research community look into that to foster the trust in such kind of methods. especially in the health domain. And with saying that, I thank you for your attention. I'm sorry for the 1 or 2 interruptions. And of course, I thank to the team who contributed to it. And I'm very happy to answer your questions.